We will build an autonomous research agent, a system designed to move past simple chat interactions and into independent, goal-directed work. By the end of this process, your agent will be able to search the web, summarize findings, and format a daily email brief entirely on its own. To begin, you'll need 4 components: an IDE, an agent framework like LangGraph or Crew AI, an LLM API key, and access to a vector database. Giving a language model access to external tools and memory shifts the engineering focus toward proactive execution. The system uses these resources to navigate toward a defined outcome without needing a human to trigger every individual subtask. This diagram maps the architecture we will follow. Every user input passes through validation, hits the agent core, routes out to tools and memory, clears safety guardrails, and finally generates an output. Match the LLM to your specific workflow constraints. For tasks involving complex coding or a 200,000 token context window, models like Claude are optimized for agentic reasoning. If the project requires local private deployment, an open source model like Llama is the viable path. Looking at this code editor, you can see a strictly formatted JSON schema. Before connecting any AI models, we must document exactly what data flows in and the precise format the agent returns. To write the system prompt, define 5 specific variables: the agent's role, the primary task, the desired tone, hard constraints, and the explicit output format. Treat the system prompt as a rigid configuration file rather than a suggestion. This level of detail prevents unexpected downstream behavior and ensures the agent acts consistently across every session. Defining the schema and system prompt at the start dictates how every subsequent tool is integrated. To connect a tool like web search to the agent core, define its name, description, and parameters. Exposing the LLM to too many tools simultaneously causes hallucinations. Use an iterative cycle. Add one tool, test it, and verify the output before introducing the next. We ground the agent in specific user data using Retrieval Augmented Generation, or RAG. This allows the system to pull from your own documents rather than relying solely on its general training weights. Architecturally, we distinguish between short-term memory, the immediate conversation history, and long-term memory, which involves retrieving facts from a vector database on demand. Vector memory transforms the agent into a context-aware system. It allows the agent to recall user preferences and past outputs, which are otherwise lost once a session ends. This flowchart shows an execution process halting at a human approval gate. For high-stakes actions like making payments or sending emails, the system requires a manual trigger before proceeding. To prevent prompt injection attacks, the system must validate all user inputs before the agent processes them. This creates a security layer that keeps the agent within its intended boundaries. In a multi-agent setup, you can optimize costs by routing the workload. Send 70. Here we see the complete life cycle. The system retrieves context from memory, uses a search tool, generates structured JSON, and triggers an external action. Binding the core logic to real-world tools and vector memory creates a system capable of autonomous task completion. As established in Anthropic's development guidelines, the most successful AI agents rely on simple, composable patterns rather than overwhelming complexity. Ship one reliable workflow first to prove its stability. Once that loop is bulletproof, you can begin to scale and add multi-agent complexity.